Today, we're going to tackle one of the most fundamental forces in our universe, electricity. We're going to connect the dots from that little shock you get from a doorknob all the way to the massive current that powers our daily lives. Let's jump in. We've all been there, right? You walk across the carpet, reach for a doorknob, and zap! You get that little surprise. Or maybe you've run a comb through your hair and suddenly it's standing on end, defying gravity. Well, those little everyday moments, they're actually our first clue to understanding the hidden world of electricity. So what's happening here with the comb and the hair? This is what we call static electricity. And it's all because of simple friction, just rubbing two things together. But to really get why that simple action has such a weird effect, we need to zoom in. I mean, way in. To understand that static cling, we have to go down to the atomic level, to the very building blocks of matter itself, because inside every single atom is a tiny, tiny particle that's the real star of our show. So, everything is made of atoms, and every atom has a core, the nucleus, with positive protons and neutral neutrons just kind of hanging out. But buzzing around the outside, you've got these little negatively charged particles called electrons. And these guys, they are the key players, because unlike the stuff in the middle, they aren't locked down. And here is the absolute key to all of this. While the protons and neutrons are stuck in the center, those electrons on the outside can be knocked loose. They're the only particle that can actually jump from one object to another. So when you run that comb through your hair, it's the electrons that are on the move. And that simple little transfer is what creates an electric charge. It's that easy. The plastic comb literally steals some electrons from your hair, so it gets a negative charge. Your hair, which just lost all those negative electrons, is now left with more positive particles, so it becomes positively charged. And this brings us to one of the most fundamental rules of physics: opposites attract. The negatively charged comb and the positively charged hair are now drawn to each other. It's not magic, it's just physics at its coolest. Okay, so we've got static charge. It's interesting for sure, but it's not charging your phone, is it? So the next big question is, how do we get these electrons to stop just clinging to stuff and start moving in a controlled way that we can actually use? How do we make them flow? The answer is an electric circuit. The best way to think of it is as a highway system just for electrons. See, for electricity to do any real work, it needs a complete closed loop to travel on, a path to carry energy from a source, like a battery, all the way to a device.
And here's what a super simple one looks like. You've got your energy source, the battery, you've got the road itself, the wires, you've got a device that's going to use that energy, in this case a light bulb, which also acts as a resistor, and, really importantly, you have a switch. The switch is like the drawbridge on our electron highway, letting us open or close the path whenever we want.
Now, you can imagine that drawing detailed pictures of circuits all the time would get pretty messy, especially for complex stuff. So instead, engineers and scientists use a universal shorthand. Every piece gets its own symbol, which creates a standard roadmap so that anyone, anywhere in the world can look at a diagram and know exactly how it works. All right, we've built the highway. But just like with real roads, you can design them in different ways. And when it comes to electrical circuits, there are two main layouts, series and parallel. And believe me, the choice between them has huge consequences. First up, let's look at a series circuit. You'll notice that all the parts are lined up one after the other, like a single file line. For the electrons, there is only one path to take. Think of it like a one-lane country road. Now, check this out. This is a parallel circuit. See the difference? The current flows out of the battery and comes to a fork in the road where it splits. Some electrons go through one light bulb, and the rest take a different path through the other one. This isn't a country road, it's a multi-lane superhighway for electrons. So what's the big deal? Why does this matter? Well, in that series circuit, that one-lane road, if a single light bulb burns out, the entire road is broken. Everything goes dark. Remember those old cheap holiday lights? That's why. But in a parallel circuit, if one bulb goes out, the others stay lit because the current just takes the other routes. And that is exactly why your house is wired in parallel. Okay, so we've got our electrons moving, and we can even direct the traffic down different highways. Now for the grand finale, the really cool part. What can this controlled flow of electrons, this electric current, actually do for us? This flow of current gets really powerful when we learn how to harness its effects. It basically boils down to three main ones, and these three effects have completely, fundamentally transformed the world we live in. First up, the heating effect. When you force electrons to push through a material that resists their flow, they have to work harder, and they lose energy. And where does that energy go? It gets released as heat. It's the simple idea that powers your toaster, your stove, and makes the filament in an old light bulb glow. Second, we have the magnetic effect. And this one is a real game changer. It turns out that a moving electric current creates its very own magnetic field. It's one of the most profound discoveries ever. If you wrap a wire with current flowing through it around a nail like this, you create an electromagnet. And that's the principle that drives electric motors and lets giant cranes lift cars in a junkyard. And finally, there's the chemical effect. You can pass an electric current through certain liquids and actually trigger chemical reactions. It's a process called electrolysis, and we use it to break down compounds or even to do something called electroplating, where you can coat an object in a thin protective layer of metal. So think about where we started, with a particle so tiny you can't even see it, the electron. We learned how to get it moving in a nice, neat circuit. And from that controlled flow, we've harnessed the power to generate heat and light, to create motion with magnetism, and even to transform the very nature of materials. From the very device you're watching this on right now, to the lights in your room, almost everything runs on these same basic principles. This journey of the electron has literally built our modern world. So the only question left is, what's it going to build for us tomorrow?